So for this particular problem, we have a bucket of mass 3.2 kilogram that is swirled at a constant rate in a vertical circle of radius 1.7 meters. And it says the mass of the quart is negligible. It's just a bucket makes 6 revolutions per second, revs per second. So this is important. All right, part A asks us to calculate the linear speed. Part B asks us to calculate the centripetal force. C, calculate the tension at point C and A. C being the bottom, A being the very, very top of the arc, and then D asks us to find the net force of the bucket at point B being directly to the left of the vertical loop here. All right, so let's go ahead and crack out part A real quick. In order to do part A correctly, you have to understand that this is given as 6 revolutions per second. This is not meters per second. Therefore, 1 revolutions is 1 lap. 1 lap is, for this one, is just the circumference of a circle, okay? So 1 revolutions is 1 circumference, so keep that in mind as I show you how to convert here. So here I have a statement that says 1 revolution is 1 circumference. The circumference of a circle is 2 pi r in mathematics. So here I'm just going to start with my given value, 6 revs per second, because that's what it says. Times it by, for every 1 revolution, it makes 1 circumference. The equation for a circumference of a circle is 2 pi r. Here I've chosen to use lowercase r. It is up to you if you want to do lowercase r or uppercase r. But so essentially revs cancels out. Okay, so the only thing left really here is 6 times 2 times pi times r being 1.7 meters because it is given in the problem. Here it says on the very top in the black here in the wording, it says the radius of the circle is 1.7 meters long. All right, so other than that, if you punch this in the calculator, 6 times 2 times pi times 1.7, you should get about 64.1 meters per second. All right, now that we have the linear speed in meters per second, let's do part B. Part B is pretty whack. It asks for the centripetal force. The function for centripetal force is just mv squared divided by r. V being here your tangential speed. So here, mass is 3.2 kilograms. The tangential speed I already found, which is 64.1. And then we're going to square that divided by the radius of the vertical loop here, or the vertical circle, which is 1.7 meters. If you punch this all in the calculator, you should get about 77,734.23 newtons. And here I include the direction towards the center. Why? Because it asked for a centripetal force. It didn't say magnitude. So the best way to express directions for centripetal force problem, it is towards the center because it is pointing towards center at every point in the vertical loop here, okay? So instead of saying left, right, up, or down, I'm just gonna say towards the center because I don't know where the bucket is at any given time. All right, now let's do C and D. To do C, it says find the tension in the chord at the bottom and the top. So point C being the bottom, point A being the top of the arc. So in no particular order, I'm just going to go ahead and knock this out. So I'm going to do the bottom first. To do the bottom first, you have to realize that at the very, very bottom of the vertical loop, the bucket has an F of G that's pointing down the page, but it also has a tension pointing towards the center where the hand is holding the string. Now, once again, I do want to point out that for vertical problems, at the very, very bottom of the vertical loop, T has to be greater than F of G because the bucket is being swung upward at this point, regardless of whether you go clockwise or counterclockwise. So T must be greater than F of G. It is a common misconception that folks might think T is equal to F of G. If they were equal, then the bucket would not be moving up or moving up clockwise or counterclockwise at all. Okay. So here I'm going to set up the physics for it. Net force is equal to the centripetal force of this particular segment or location, point C. At point C, I have T, which is greater, which is pointing upward, subtracted from F of G because both these vectors lies in the y-axis at this particular point. So here in my work, I have T minus F of G, which is equal to F of C. But we're asked to find the tension, okay? So to find tension, I want to move this negative F of G to the right, which makes it positive. So here T is equal to F of C plus F of G. But I already know what F of C is. I just calculated in part B what F of C is, which is 7,734.23. Well, F of G is super light work. F of G is just mass times gravity, okay? So here, I just carry the value for F of C, which I got here in green, 7,734.23 newtons. That's the magnitude, plus F of G. But F of G is just mg, and if I plug in m being 3.2 because it's given, g being positive 9.8 here because I've already taken care of the negative sign in my work. So here for g, I'm just going to plug in 9.8. So if you add those two values up, you get 7,765.59 newtons. So this is the tension at the very, very bottom of the vertical loop at point C. Okay. Now, well, I did the bottom already. So here in part C, it's just the bottom and the top. So let's do the top. At the very top, you have FG pointing down again. So FG always directs down the page. So here's FG pointing towards the center circle. But at the same time, when the bucket is at the very, very top, the hand is pulling, quote unquote, down on the bucket. So the tension in the string must be pointing down towards the hand. So therefore, at the very top, you have FG plus T because both these vectors are pointing in the same direction. And that is your net force. Your net force here is your centripetal force. So therefore, for net force, I just plug in T plus F of G, which is equal to F of C. So in this case, I'm just going to solve for T by subtracting both sides by F of G. So therefore, I'm going to move this positive F of G to the right side of the equal sign, which makes it negative. And then now, once again, I already know F of C, right? Part C is kind of leading you towards part B is leading you towards part C and D here. So here, I'm just going to use the value that I calculated for F of C already in part B, which is 7,734.23 newtons. So I forgot the capital N there for newtons, but please fill that in. And then minus F of G is mass times gravity, mass being 3.2, gravity being 9.8, because I've already taken care of the negative sign. And then if you take the difference here, you should get about 7,702.87 newtons, which makes sense, right? The tension at the bottom of the loop should be greater than the tension at the top of the loop, okay? So just keep that concept in mind. The tension at the bottom of the vertical loop is always greater than the tension at the top of the loop, because as it goes up, the tension in the string tends to releases a little bit, okay? All right, that takes care of A, B, and C. Let's go ahead and do part D, okay? Part D, asks us to calculate net force acting on the bucket at point B. So this one's a little tricky. So at point B, you should then definitely identify your free body diagram again. So here I have T pointing towards the hand because that's where the string is being pulled, and then F of G is pointing down the page as usual. But you notice here T and F of G are not in the same axis, right? T is pointing to the right, which is in the positive x-axis, and then F of G is pointing down along the page, which is in the negative y-axis. So to find the net force, we have to really draw our net force vector here. This T is pointing right, F of G is pointing down, so my net force is going to be pointing down and to the right, which is here, this vector here, that's pointing, quote, I would like to call this in the fourth quadrant, if you're referencing the bucket, right? Because T is pointing right, F of G is pointing down, so the vector for the net force has to be in this particular quadrant. Again, this is not drawn on scale here. So to find net force here, I have the adjacent and the opposite. I need to use Pythagorean theorem. So ultimately, I have a right triangle. So net force using a Pythagorean theorem is equal to net force squared is equal to net force in the x direction squared plus net force in the y direction squared. So it's like c squared equals a squared plus b squared. Why? Because you have a right triangle. All right. So in order to do so, I need to identify what is my net force in the x direction. So if you look at this diagram correctly, net force in the x direction is my t. Hence, I replace f of x with just t, and I want to square that. In the y direction, it's just f of g, so I want to replace net force in the y direction, which is f of g, so I want to square that as well. So here we have t squared plus f of g squared. Well, I can figure out what t is, right? At this location, t is my centripetal force because it is the only vector pointing towards the center, pointing towards the hand where the hand is pulling this particular bucket. Well, I know F of C from our previous work in part B, so if you need to rewind the video, is 7,734.23 newtons. So I already know what T is. Well, F of G is super light work, right? F of G is just mass times gravity, mass being 3.2, G being 9.8. So here, F of G is 31.36. I understand it's negative, just so you know. Like, this is pointing down, right? So we say it's negative. However, if you look up Pythagorean theorem, you're going to square it anyway, so it doesn't really matter, okay? So here, what I've done is I've just carried my work down. Net force squared equals t squared plus f of g squared. Well, I know what t is, which is 7,734.23. There it is. I want to square that. I want to add it to f of g, which is 31.36 squared. So if you plug all this in, you should get a massive number, right? This 9297.14 newton squared. And then to solve for f, or net force, we need to take the square root of both sides. And if you take the square root of both sides, you get about 7,734.3 newtons. And this value is pretty close to the centripetal force, right? Because if you look at it, mathematically speaking, the tension here in the string at point B is already 7,734, but the weight of the bucket is only 31.36. So right away, T dwarfs F of G, right? You got 7,700 here, and you only got about 31 here. So if you think about a right triangle, you got 7,000, and if you open up the triangle, and this is only 31, it produces this really small angle. So here I found net force for you. Net force here is 7,734.3 Newton, but this is just the magnitude. Well, if I'm reading part D correctly, it says find the net force. It never uses the word magnitude. So I need to give, the direction, because force is a vector. It has to have a magnitude and direction. So doing Pythagorean theorem only allows you to find the magnitude, but I can find the direction super quick. So to find direction, I want to shift this f of g to the right. Again, you don't have to, but I'm doing this so I can see it's a right triangle, right? So watch my animation again. I'm going to move FG back where it was in the diagram here, where I'm kind of going back and forth here. I want to move f of g vector to the right. I'm not tilting it, so I can literally cut it and shift it as long as I don't tilt the arrow. It stays the same. Well, here's theta. Okay, theta here touches the horizontal axis. Well, I know what t is, which is the adjacent to this theta. I know what f of g is, which is the opposite. So right away, I know my adjacent, I know my opposite, so I can use tangent. So I'm going to apply tangent because I know both the legs. Tangent of theta, this theta here, is equal to opposite, which is f of g, over adjacent, which is t. F of g here goes on top because that's my opposite, t being my adjacent. Well, to find theta, I need to take inverse of tan. Well, what's f of g? F of g we calculated already here. It's 31.36. Well, what the heck is t? T is 7,734.23, which is right here for you. Right? It's the centripetal force at location B, which is perfectly to the left in the midpoint. All right, once you do that on your calculator, you should get a really small angle of 0.23 degrees, which makes sense because 31 over 7,734, it's a pretty dang small number. So the angle is going to be super small. And here I said southeast because this net force vector here, once again, is pointing right, which is east, and then it goes down, which is south, so southeast. And so to provide the proper answer, I would say the net force is 7,734.3 newtons, and its angle at 0.23 degrees southeast. And that is my final answer. All right, I hope that makes sense. Stay nerdy, don't be whack.